So what is a decision tree? Decision tree is one of the supervised machine learning algorithm. It is used for solving both regression as well as the classification problem. Okay. It basically the decision tree, it follows the if-else conditions. Okay, it follows a set of if-else conditions to visualize the data and classify it according to the conditions. Okay. The decision trees are non-parametric supervised machine learning technique. What do you mean by non-parametric? It is nothing but that, like the linear regression, logistic regression, decision tree does not make any assumption. Hope you remember in linear regression, though your adjusted R squared metric value is very high or RMS is very less, still you are supposed to validate your model assumptions like linearity, homoscedasticity, and multicollinearity, autocorrelation, right? All those things, whether the residuals are normally distributed. So you need to validate those assumptions in addition to the error metric as well as the adjusted R squared metric. When it comes to decision tree, it doesn't make any assumption like linear and logistic regression. So that is what it says, non-parametric supervised machine learning technique. So using decision tree, we can build classification or regression models in the form of a tree structure. We can see the decision tree is constructed in a top-down recursive manner. Using decision tree, we can classify, the algorithm classify the instances or examples by starting at the root of the tree and moving through it until a leaf node. Okay. Now let us try to understand what are the advantages of decision tree. It is very easy to understand and interpret. Even a layman, when he looks at the decision tree, he should be able to gain insights from it. Okay, it is very easy to understand. That is one of the important advantage of decision tree. And using decision tree, you can generate the rules. In R, there are some packages are available using which you can generate the rules from the decision tree. And especially when you are working with the huge volume of the data and the number of features are more. The more the number of features, though you can view the decision tree to infer the insights, right? You gain the insights, but still there could be chances that you might tend to miss out certain rules, right? Especially if you have 25 to 30 or 35, reasonably 35 features are there in your data set. Your tree will have more number of features, more number of branches, more number of subtrees. In that case, you might tend to lose track, or you might tend to make a mistake, or you might tend to disregard certain rules. That is where generating the rules, packages, there are packages that are available to generate the rules from the decision tree so that you will not miss out any of the rule. And the decision tree does not require too much of data preparation. You don't have to prepare exhaustive, you don't have to spend exhaustive time in terms of preparing the data. When it comes to other algorithms, yes, you need to address the outliers and you need to address the missing values. In the case of linear regression, it is prone to, in the case of linear regression, if you have outlier in your data set, it is prone to, it is sensitive to outlier, basically the linear regression, right? And also if you have missing values, you need to address it. But when it comes to decision tree, you don't have to address outliers and missing values. It takes care automatically. And importantly, it doesn't, it is not bounded by any data types. You can use any data type. Your features or labeled output feature, right? Or your features can be any data type. In the case of linear regression and logistic regression, all your features are supposed to be quantitative, numerical value. In case of any categorical variable, if you have any categorical variables are there, you need to convert that to numerical variable. That is the prerequisite for linear and logistic regression. When it comes to decision tree, the data type of your features can be anything. And also it is non-parametric, as I told you, right? It doesn't make any assumption. And one of the disadvantages with decision tree is it is prone to overfit. It is prone to overfit. But anyway, we don't have to worry about the overfitting because there is an option called pruning, right? You can chop the tree. You can chop the tree from. So basically, we have some option to find out from which part of the tree it starts doing overfitting. Okay, for that we have some option called pruning. Using pruning, you can address the overfitting issue. Now let us dive into understanding the terminology used in decision tree. Okay, so this is the decision tree. This is how the typical decision tree will look like. I took only a simple data set so that you can understand without much pain. Okay, so here I have 4 columns here. Of the 4 columns, we have 3 features: the gender, income, and age. Here the gender is the root node, right? This is the one is called your root node. So this is the one, in this case gender, right? Gender is the root node. So this is the one is used for, gender column is used for dividing the data into 2 or more sets. Right? So this root node column gender is determined based on certain algorithms. We have something called Gini index, Gini split, and entropy, information gain, and we have something else called reduction invariance. Using those techniques, it will be determined of the given data set which column is supposed to be used as a root node, which all columns that are supposed to be used as a branch node. Hope it's clear, right? So in this case, gender is the root node. So this gender column is used for dividing the data set into 2 or more sets. In this case, gender, how many classes are the categories? Only 2, male or female. So on the left side, let's the female, right? So the female, it's splitted, the gender column splits the entire data set into 2 parts, male and female, right? So in this case, okay, female. Now what will happen is only the female data, the subset of the female data will be available on the left side. Okay, so within this female income, we are checking the income column. So this is called your decision node or branch node. So in the income, once again we are splitting this one. The algorithm splits the data based on the category here. It need not to be a categorical variable, it can be a numerical value also. Okay, so here in this case, let's say the income is medium, the last column is by. So what does that says is, what it says is, those female customers with the medium income, they do not buy. Let's say we are launching a new offer. Before we launch a new offer, we want to make a prediction. Once the new offer is rolled out, what are the chances that the customer is going to buy? Which all customers are more likely to buy? So if you look at here, as I told you, decision tree is very intuitive one and very easy to interpret this one. Look here. If you look here, a female with higher income, they are more likely to buy. So here the female with higher income, only one person is there. Only one customer with higher income is there. She is more likely to buy. On the other hand, 2 females, they have a medium income, they don't buy. Okay, since the condition is true, on the left side for female, it subsetted the given data set based on the female data set, female category. Within that female category, once again it partitions the data. So based on high and medium. So usually you need to keep that in mind for anything greater than, right? So in this case, it is a categorical variable. Let's see if the income is a quantitative variable. In that case, if anything is greater than, right, that's what I mentioned. It will be, it will be branched out on the right side. Right? When the decision tree is numerical, when the decision is numerical, the greater than branches usually show on the right and less than on the left. Okay, just keep that in mind. Okay, and this is called your leaf node. This is the the last node in your decision tree. No matter the size of your tree. Okay, you take any size of the tree, the bottom one, right? The bottom one is called your leaf node. Just beneath the leaf node, you will not see any more branches, any more leaves. This is the last node in your tree. It is also called as a terminal node, and right, some people they call it a leaf node. In general, they call it as a leaf node. The leaf node will have either the predicted label or it can have the probability score also. So if you don't want the predicted class label, if you don't want the class label to be predicted here, right? So it will assign the probability. For example, there is a 0.8 probability female customers with higher income, they are more likely to buy. There is a 0.2 probability the female with medium income, they will not buy. Okay, so here either you can, or you can have the combination of both. You can have the combination of both. I'll show you, I have another example, I'll show you there. At this moment, try to understand what is a branch node, what is a root node, and what is the depth. From the top level, the depth is 1. Supposing I have another subtree like this, age like this, right? If I have another subtree like this, the depth is 1 to 3 for that. Let's say age is another column is there here, another red colored one here. That means 1, 2, 3. From the root node, the depth of that node is 3. Depth, it says, what is the depth of the node from the root node. And this is your leaf node, and this is a branch node. Branch node is also called as your testing point, right? That is how they call it. Now let us take one the sample data set. This is the one I discussed as part of NAEBase. Any of for Rajesh and other people, right? I'll just cover it once again. Okay, before I jump in with this data set to explain how the decision tree is constructed, I have one question here. Okay, here I have used gender as the root node. Now the question is, why gender supposed to be a root node? Why can't it be income, or why can't it be age? Or is it because the gender column is located in the first position of the data set, the gender has been considered as root node? No, it is not. It is not the fact that the gender column is located in the first column, it is considered as a root node. Okay, the root node, the column for the root node is determined purely based on the algorithms like Gini index, okay, or Gini index or something else. Okay, Gini index, other thing. It is a common segregator for all the data. No, it is not common segregator. Yeah, root node is the common segregator. Yeah, we can make it, if you want to make a generalized statement, yes, root node is the common segregator. But so which column should I use it? Can I use gender as the root node, or can I use income or age? Of all these three features, which one should I use it as a root node? Okay, so it is not like I can use any column. It is purely based on certain algorithms. Okay, so that we will see how, which algorithms are supposed to be used in order to choose. Okay, let's say let's assume that as per the algorithm, the root node is gender. My algorithm says use gender column as a root node. The next step is, we have two more features. Of these two features, which one should I first use the branch node? Can I use this one or can I use this one? Right? The order of partitioning the features is purely based on the various approaches like or techniques like Gini index, those things will say. So for that, I'm going to use this data set. This is a very simple data. Look here, these are the, forget about the ID, okay? We have 14 observations are there here. And we have 3 features. These are the independent features. And this is my dependent variable. It's a binary categorical variable. A person by the name of John, right? So he played tennis under different circumstances of the weather, right? With the different combination of weather, with the different weather combinations, he played tennis, and with the different combination of weather, he did not play tennis. Okay. So if you look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Out of 14 times, right? 9 times he played tennis for the different weather conditions. When I plotted, when I use this data set to fit my decision tree model, and when I plotted this, right, visually it looks like this. Outlook. What is outlook? Outlook is kind of, weather, right? Outlook is weather, and in the outlook, rain or sunny, and if it is humidity, look here, yes or no. As I told you a while back, you can use the decision tree to predict the class level, and also you can assign the probability. But in this case, the model, right, the model assigns the predicted class level as well as the probability. So what we can understand from here is, when the outlook is sunny and rain and the humidity is high, there is a 0.2 probability he played. There is a 0.8 probability he did not play. That is what it says. Very easy, right? Very easy to interpret. And similarly, if you look here on the right side, when the outlook is rain and sunny, and the humidity is normal, when the wind is strong and the outlook was rain, he did not play at all. But here, see, multiple conditions you can check with the different combinations. What are the chances that he played or not? Look here, in this case, the wind is strong and outlook was sunny. That in that case, what happened? There is a 100% chances. That means, he played tennis with probability 1. There is 100% chances that he played tennis. Similarly here, right? So the humidity is normal and the wind is weak. He played, right? So the probability is 1. The chances of playing tennis given this weather condition is 1. But when you look at on the right side of this one, if you look at this one, the outlook is, when the outlook is overcast. Overcast is nothing but cloudy weather, right? Cloudy, okay? So in the case of outlook, he played tennis. But here yes or no is there, right? The dark colored one is yes. The light colored one is no. There is a right? There is a probability. There is a higher probability, right? So you play tennis. That is how you need to interpret from this one. It's very easy to interpret. Once you fit the model and you plot the decision tree, very easy to understand. Now the question is, again I am coming back to the same thing. Why outlook should be the root node? Why can't it be the humidity? Right? So before we understand that, right, let us try to understand how the decision tree partitions the data. So let it be there, okay? The outlook is the root node, right? So in the case of outlook, how many categories are there? How many categories are there? How many categories are in outlook? Sunny, unique categories, sunny, overcast, rain. Only 3 categories are there. Yes, only 3 categories are there. Sunny, overcast, outlook. So what happened here? It it subsetted the data, right? It subsetted the Outlook root node based on the three categories. In Sunny, how many yes is there, how many no is there in the target column? You need to compare with the target column. See, for the sake of for illustration purpose, I just put the subset of this data here itself. Okay, I just copy pasted here the subset of the data. So in the case of in the case of Outlook column, how many number of Sunny records are there? 5 observations are there for Sunny category. Within this Sunny category, how many yeses are there, how many no's are there? You need to look at the target column. This is my dependent variable, right? Look at the, so how many yes is there, how many no is there? 2 yes is there, 3 no is there. That's what I mentioned here. Similarly, when you look at the overcast, this is the data set. Within this overcast, you need to look at the target values. How many yes is there, how many no is there? 4 yes is there, there is no, right? We don't have no here. Hence, we call that as a pure node. Remember this. This is called pure node, but this is not a pure node. This is called, the Sunny node is impure. Okay, next we will see rain. In the case of rain also we have 4 observations are there. In total, how many observations we saw? 5 plus 5, 10 plus 4, 14. Yes, correct. For rain, 5 records are there. In the case of rain category, 5 observations are there. If you look at the target column values, we have 3 yes and 2 no. We have 3 yes and 2 no. Fine. Okay. The next one is, so what happens? The next one is, look here, in the case of pure node, this is called pure node because here we don't have the mix of both yes and no. We have only yes, hence it is called pure node. In the case of pure node, it doesn't require further split. It doesn't require further split. Look at here the Sunny and rain. These two nodes are not pure node because it has a combination of both yes and no. Look here also yes is there, no is there. Since it has the combination of both yes and no, these two nodes are impure node. The impure nodes will undergo further split. The next question is, how many number of splits will happen? Let's say this is impure node, this node is impure node. This one will undergo further split iteratively as long as the node becomes pure, right? As long as the node becomes pure. So now within Sunny, look at this column. This is my humidity column. The second column is the humidity. Within humidity, how many categories are there? Only 2, high and normal. Within, right? So now, based on the high and normal, it splitted it further, right? So high has only 3 no and normal has only 2 yes. Since these two nodes doesn't have both the combination of yes and no, right? These two nodes became pure node, right? Now let us look at on the right side. The same thing is happening. In the case of the rain node, what happens is this one is the wind column, right? Already this has been done here. Next one is wind. This one is the wind. Okay, wind. In this column, how many number of categories are there? Distinct categories. Only 2 categories: weak or strong. But if you look at the target value for the weak and strong, weak has only yes, yes, yes only, and strong 2 no, no is there. So this one, right, splitted this one into 2 different categories here. So here the weak has 3 yes and 0 no, and strong has 0 yes and 2 no. These 2 nodes also now became pure node. In simple term, your training data starts from the root node and it splitted the data based on the category of your root node column, and each subset again it tries to partition the data, recursively until the data become, until the nodes become pure. So now what happens, if you look here, these two nodes are pure, because here you have only yes is there, right? Yeah, no is there. Here only no is there. Here you have only yes, and here you have yes, 3 yes and 2 no. Hence these two are pure subsets. This is your leaf node. It doesn't record any further split because this is your leaf node. Leaf node is the pure node. Okay. This is how it splits. Okay. The next question is, okay, how does this knows, right, whether you know this has 0 yes and 3 no, right? So for that what we do is, you know, we use something called the decision tree. What it does is it can use either Gini index or it can use some other algorithm. Okay. So what is Gini index? What is Gini? Gini is nothing but the probability of correctly labeling a randomly chosen element. This Gini, right? This is the one helps us to selecting the split, which results in most homogeneous subnodes. Look here, in this case, you know, these nodes are homogeneous, but this node is heterogeneous because it has a combination of both yes or no. This is an impure node, whereas here it is pure node. And the decision tree splits the nodes on all available features. Okay, now let us try to understand the properties of Gini. Okay, Gini impurity is nothing but 1 minus Gini. Now let us directly jump into the formula so that you will be able to I'll jump into the workings of this one, okay, or the formula here instead of talking too much on the definition part. There are 3 steps here. Okay, well, the first step is, right, you need to calculate the Gini impurity for subnodes using this for 1 minus Gini. What is Gini? Gini is nothing but 1 minus probability of class 1 squared minus probability of class 2 squared. If you simply plug in the value for the Gini here, you will get Gini impurity. Right? So that's the next. What you need to do is you need to plug in the Gini value here, right? Gini value here, and yeah, 1 minus this one. Okay, 1 minus Gini is nothing but Gini impurity. Okay, that is what this one. Okay, and here Ni minus N, for each and every observation you need to do Ni divided by N into Gini. Okay, what is Ni? The number of records at child I and number of records at node P. But still it will be confusing. Better we'll directly jump into an example so that you'll be able to understand very clearly. So what is the formula for Gini? 1 minus Gini. So what is Gini? 1 minus Gini, right? Gini is nothing but the class 1 whole square minus class 2 whole square. Now let us look at this one. Tell me how many classes are there here? We have only one class. Class 1 we have 6 observations, yellow color. Class 2 we don't have any other circle other than yellow, hence class 2 is 0. We are talking about binary classification, okay? And if you plug in this value in this formula, so 1 minus 6 divided by 6, total number of observation is 6, and class 1 we have 6 divided by 6 whole square minus, in class 2 we don't have any observations, 0 divided by 6 whole square is equal to 0. Sorry, somebody is trying to reach me. Okay, so here 6 by 6 is 1 squared is 1, so 0 divided by anything is 0, and 1 minus 1 is 0. So this node is pure node, the 0 impurity. This node does not have any impurity, which means it is a pure node. So that is what I discussed about here. The overcast is a pure node. Right? This is pure node, and then if you look at this one, how many values are there for class 1? 5. And class 2 we have 1. We have two classes, yellow and red. And if you plug in these values in this formula, you will get 0.167. Since we have only one value for the class 2, the impurity is low. As you keep increasing the class 2 values, the impurity goes high. Look here, your class 2 we have 2 observations are there. But when I have one observation in class 2, the impurity was low. But as I keep increase the class 2 on par with, see, look at here, both of them are equal. The class 1 also we have 3 and class 2 also 3. Here the impurity is very high. Impurity is very high. Just keep that in mind, okay? So now let us look at this example. Here we have class 1 is equal to 3 and class 2 is equal to 3. So on the left side, right, this is your left side of your node, this is your root node, this is your left side of the node, branch node, another branch node. If you look here, in class 1, see in this time, now I say, here I meant class 1 is nothing but the yellow one and class 2 is 3, right? Yellow is 1 and red is 3. On the right side, class 1 is 2, class 2 is 0. If I use the Gini formula for the left side node and right side node, I get these values 0.375. Both of them are impure. And finally, I need to use this equation. Look here, Ni divided by N, right? Which is nothing but the 4 observations on the left side divided by the total number of observations. 4 Ni divided by N. So 4 divided by 6 into your Gini left. What is the Gini left value? 0.375 minus the 2 divided by 6, Ni divided by N. N is total number of observations. On the right side of the node, number of observations on the right side of the node divided by total number of observations. So 2 divided by 6 into Gini right, 0.25. So you will get 0.25. Okay, this is how we compute the value for the Gini split. First, what we did, we just computed the Gini impurity. This is nothing, this value gives you the impurity. And finally, what you need to find out the weighted average for the Gini. Okay, that's what we are doing. So 4 out of 6 into this value and 2 out of 6 into this value, it gives me the weighted average for the Gini. So lesser the Gini score will lead to further split, or the lesser the column or the feature which has lesser Gini score, that will first undergo the split. If I have multiple columns, or let's say 3 columns are there. Of the 3 columns, column A has lesser or column B has lesser Gini score, then the second column will undergo the split fast. Now let us work on one simple exercise. Use the same formula. Probably you can take one pen and paper, okay, and you tell me what is the answer for this one. Look at this one. Let's say don't go literally by this image, okay. Students, total number of students, 30 students are there, and out of 30 students, 50 students they play cricket. What is the ratio of students that they play cricket? 15 out of 30 is 50%. 50% of the students they play cricket. Okay, this is my root node. Okay, and here this is my gender. Okay, this is my gender is my root node. Let's assume that way. Okay, and the left side, right, is splitted. The gender column got splitted as female and male. In the case of female, 10 students are there. 10 female students are there. Out of the 10 female, 2 female they play cricket. So what is the ratio of the female student they play cricket? 20%. 2 out of 10 is 20%. Similarly, male. See, out of 30 students, 10 students are female and 20 students are male. Out of the 20 male student, 13 male student they play cricket. So what is the ratio that male student play cricket? 13 divided by 20 is 65%. Fine. Next, I have another column called class. We have a column called gender. We have another column called class. Right, so we have 10th standard student and 9th standard and 10th standard students are there. Okay. In the 9th standard, 14 students are there, and in 10th standard, 16 students are there. Okay. 6 students, they play cricket. Then what is the ratio that 9th standard student, they play cricket? 6 out of 14, that is your 43%. Similarly, we computed this one. Okay, 9 out of 16 is 56%. Probably you can take the calculator and check it out. Okay, now we need to calculate the Gini for the subnode female. How do you calculate the Gini for the subnode, female subnode? 1 minus class 1 whole squared minus the class 2 whole squared, right? So here calculate the Gini for subnode female. Here so here we have 10, right? So out of the 10, only 2 play cricket, remaining 8 they don't play, right? So there are 2 classes, play, not play. Play, not play. There is a 0.2, which is right, 20%, which is nothing but 0.2 probability, right? 0.2 probability. In class 1 we have 2 students. Class 1 whole squared is nothing but 0.2. 20% is nothing but 0.2, right? Class 1, and listen, class 2 is 0.8. So what is the formula? 1 minus class 1 whole squared minus class 2 whole squared. So what I am going to do is, here, listen very carefully, very simple formula. Okay, so 0.2 into 0.2. This is the formula, right? Forget about 1. I am not going to subtract this one from 1 now. So the class 1 whole squared minus class 2 whole squared. Don't get confused with this class. I am talking about category. Okay, out of this 10 female student, 2 students they play cricket. Those 2 students I call that as category 1. Listen, category 1 or class 1. Class 2 is those do not play cricket. Those do not play cricket is 0.8. Those play cricket is 0.2. There are 2 classes are there. As per the formula, we need to square it. In class 1, 0.2 into 0.2. And in class 2 also we need to do 0.2 into 0.2. And finally we need to subtract them from 1. Okay, so we need to see, when I do this, right, when I solve this, I get 0.68. 1 minus 0.68, 0.32. This is the Gini for my subnode female, 0.32. Similarly, what is the Gini for subnode male? How many students they play cricket? 13. They are class 1, which is nothing but 0.65. 0.65 into 0.65 plus the remaining 7, remaining 0.35. 0.35 is they don't play cricket. 0.65 into 0.65, they don't, they play cricket. They play cricket, and remaining 0.35 they don't play cricket. This is class 1 and class 2. So in square, we need to square this one. So when you solve this, you get 0.55. And if you subtract this, 1 minus Gini, this is nothing but your Gini. 1 minus Gini is 0.45. Next, we need to compute the weighted Gini for this one. Not for class, this one, okay. So 10 out of 30 into 0.32. And here we have how many records are there? Here, yeah, in this side, okay, 10 out of 30 into 0.32, 20 out of 30 into 0.45. So how much you will get? How much you will get? Can someone help me out on this one? How much you will get? Why don't you use calculator and tell me? Prakash, why don't you tell me now? It is 0.40. It is 0.4026. Correct me if I am wrong. Next, what I am going to do is, so far we played around with this gender node only. For the female node, we calculated the Gini, and for the male node, we calculated the Gini impurity, and finally we did the weighted average for the Gini split for the gender. Next, we need to do the same for the class column. Now you tell me what is the weighted Gini for the split class. Okay, this is for gender, sorry. Okay, I'll just correct it now itself. Next, what is the value for the class? Anyhow, I will just do it on your 0.43 is class 1 and class 2 is remaining, right? Remaining value is your class 2. Remaining is 0.57. Okay, here, okay, there is a mistake here. It's correct only, right? Yeah, 0.57, correct. 0.57. The play cricket, do not play cricket. For the class 9 and class 10, play cricket, do not play cricket. Play cricket is class 1, do not play cricket is class 2. You need to square these two and subtract this one from 1. Okay, 1 minus 0.51, 1 minus 0.51. When you plug in these values, now what we need to do is 14 out of 30 into 0.51 plus 16 out of 30 into 0.51. I get the weighted Gini for the class column is 0.80. Now I am going to ask you a simple question. We computed the weighted Gini for class as well as gender. Of these two, which one is a lesser value? Which one has a lesser value? Obviously gender. Gender, the weighted Gini split value is 0.40. Compared to class, the gender weighted Gini value is much lesser. Hence, what we conclude here? So what we conclude here is the column, the feature which has lesser weighted Gini, that is the one has to undergo the split first, and then only this one should undergo the split. Now you would have understood the basis for splitting the order of splitting the columns. First, gender has to be splitted because gender column has lesser weighted Gini value compared to class, and this one has to undergo the split first. Okay, this is how. Now I just summarized here the split on gender column and class column. See, gender column and class column, the gender is we got 0.40, the weighted Gini, and for class I got 0.80. The Gini index for gender is less, and gender will be the first split of the decision tree. It is very simple. Next, similar to Gini, we have something else called entropy and information gain. Either the decision tree model can use Gini index or Gini weighted Gini split to determine the order of the columns that needs to be splitted, okay, or which order the column have to be splitted. We have similar to Gini, we have something else called entropy and information gain, but keep that in mind. Gini split, we do it. Now let us go back to this one. the definition a little bit, because you need to remember certain things. With the example, you are able to understand. Gini is the, what is Gini? Gini is the probability of correctly labeling a randomly chosen element. Selects the split which results in most homogeneous subnodes. Decision tree splits the nodes on all available features. Lower the Gini impurity, higher the homogeneity of nodes. We used gender as well as class columns, those two features. Of those two, the gender column has lesser Gini impurity. That means that column has higher the homogeneity. It works only with categorical binary targets. This is very important. Gini works only with binary categorical variable. If you have multi-class variable, then you cannot use Gini. That is what I am trying to say. CORT uses Gini method. There is an algorithm called CORT. CORT stands for classification and regression trees. As I told you, we can use decision tree to solve both the classification as well as the regression problem. To solve a regression problem using decision tree, we call this a regression tree. What is a regression tree? Which is nothing but the tree is used to solve the regression problem. Classifier, we say classifier. Classifier is nothing but solving the classification problem. CORT stands for classification and regression tree. Both of them uses Gini method. And this is the formula. I discussed it. Next, entropy and information gain. How does this technique works? So even this entropy works only with categorical targets, binary categorical targets. Entropy based methods are one common way. This is the formula used for entropy. Entropy is equivalent to H is equivalent to negative value for each and every class. Probability of class into log 2 of the probability of class. Here the P is the probability of target event and C is the number of choices in target event. If the value of entropy is equivalent to 0, that means it's a pure node. Okay. Either the probability of class is 0 or 1 for any class. In that case, right, the H equal to 0 is a pure node. Sorry, so for binary classification, H equal to 0 is a pure node. Okay. Anyhow, I will revisit this definition after I explain this with some example. Okay, so that with example you will be able to understand the definition. Okay, lesser the entropy, higher the homogeneity of nodes. Same as Gini. Lesser the weighted Gini, higher the homogeneity of nodes. That means that doesn't have the mix of both yes or no. Calculate the entry of entropy of each child node subset of the data. So ID3, there is an algorithm called ID3 that uses entropy method. So now let's try to understand information gain. Information gain. See here I mentioned about entropy and information gain. To compute the or to get the value of information gain, you need to subtract entropy from 1. You will get information gain. Enough theory. Let us take some example and then we'll understand how it works. Look here. I just copy pasted the same data here. The John playing tennis, right? What is the chances? What is the probability John will play tennis? Or right, that is the one I discussed. Even the case of Gini, I did not. There I used played cricket. Let's use tennis data set. Okay, here given the so and so circumstance, he played certain weather condition, he played tennis, certain weather condition he did not play tennis. Now let us use this formula and we will try to find out of these three features, outlook, humidity and wind, which feature is candidate for root node. Of these three features, which node is eligible for root node? Now let us use this formula. So 9 out of 14. Let us look here, the target column. Out of 14 records, how many S's are there? 9. 9 out of 14 times he played 10 S. So you need to use negative here. This is the formula. Okay, 9 out of 14 into, this is the entropy. You remember entropy here, the formula minus the class into log of this class 1 minus the class 2 into log of class 2. Okay, so here the same value we are plugging in here. So what are the chances that he did not play tennis? 5 out of 14 chances that he did not, or 5 out of 14 times he did not play tennis. Same thing you are putting it inside the log, because this is the formula. If you solve this, you will get 0.940. This is your entropy. This is the common value, okay, common for all the cases. For all the cases overall, okay, just we looked at the target variable, we computed the entropy. Next, we iterate through each and every column. Let's take the first column, outlook. In outlook, how many distinct values are there? Sunny, overcast, rain. Right? In sunny, we have in total 5 records are there. That's what I discussed I know a while back, right? In sunny, we have 5 records are there. Of the 5, we have 3 no's and 2 yes. Look here, sunny 2 no and sunny 3 no. And sunny we have 1 yes, other yes, 2 yes and 3 no. So first we start with yes, and next one is no. 2 out of 5 times during sunny times he played tennis. 3 out of 5 times during sunny he did not play tennis. Simply plug in the values, you'll get this one. Similarly for overcast, take filter only the overcast. As we saw earlier, overcast subset of the data is the pure node. It doesn't have both yes or no. If you plug in here, so 4 out of 4 record into 4 out of 4 time he played tennis during overcast. 0 out of 4, right? 0 divided by 0 is 0 by anything is 0, right? So this is 1 minus 1 into log of 1. Log of 1 is 0, right? So log of 1 is 0 by default. Okay, so 0 into 0 is 0, and this one is 0 minus 0 is 0. Similarly rain, we will compute for rain. If you take the rain, we have 5 observations are there, right? If you look at 3, 4, 5, out of 5 observations, the 3 times he played tennis and 2 times he did not play tennis. So yes is 3 out of 5 and 2 out of 5. For each and every subset in this column, we computed the entropy. This is called your entropy. H is entropy. The entropy of sunny, entropy of overcast, entropy of the rain we computed, and the overall for all the classes, right? Overall entropy also we computed. Next, what we are going to do is we are going to substitute everything in this one, right? Entropy, right? Entropy minus each and everything, you will get 0.94, 0.246. Okay, 0.94. This is the overall entropy value. You remember? So 0.94 minus 5 by 14. 5 out of 14 record into 0.971. 4 out of 14 into 0 plus 5 out of 14 into 0.97. That is how you need to use. This you need to remember. This is your information gain. Okay, this is how you need to compute the weighted information gain. In the outlook column, we have 3 subsets. For each subset, we computed the Gini value 0.971, 0 and 0.97, but weighted gain, weighted entropy, you need to do it, right? So 5 out of 14 into this one, and 4 out of 14, 5, and then you need to subtract this one, overall entropy. That is how you will get the gain, 0.246. So now to get the information gain value for outlook column, we followed these many number of steps. Like how we computed the information gain for outlook column, we have to compute the information gain for the humidity and wind also. Here I already did it. Okay, the information gain for outlook is 0.246 and for humidity is 0.048 and for wind 0.029. Now you tell me, out of these three values, for these three features, which feature has higher information gain? Which one has higher information gain? Wind? Oh, this is the previous one. Okay. No. You tell me. It's not wind. Which one is bigger value of these three? Yes, Rajesh. Yes, Bhupati. Yeah, outlook, right? Outlook of these three, outlook column information gain is very high. Hence, outlook column will undergo the split first. Since this is right. Since we are going to build a new tree, this is going to be the root node. The remaining two columns, which column has higher information gain? Forget about this one. See now, since for these three columns, outlook column has higher gain. Hence it is a root node. Now the algorithm has to determine the remaining of these two, which one has to be considered the branch node. Again the same rule. Humidity, very good, right? Humidity, correct. Of these two, this one is has higher gain. This is the order. Okay, this is the order. This is how the order of the splitting is happening. It is not based on the position of the column in your data set. Don't think just because outlook column is the first column, it considered as the root node. No, you need to find out the root node. You need to perform this many. You need to perform this much of math. Okay. So of all the three columns, the information gain for outlook is very high. Hence, this is considered as the root node. And the next column is humidity. Since humidity gain is more than this one will undergo next split. Okay, the third split is this one. This is how the order of split is happening. Okay, now the question is, we discussed about Gini impurity and also we discussed about information gain. Now the question is, what is the difference between these two? When should I use Gini? When should I use information gain? It is pretty straightforward. Look here, right? When you use Gini impurity, you need not to perform log and all, right? When you use information gain in the formula, they are using log of something. Since logarithm is used, it is computationally intensive, hence Gini is far better. Gini impurity is far better. But still, we can specify it as an parameter. So we have some option in the decision tree. We can specify what type of the impurity method you can use it. Whether you want to use Gini or you can use information gain. I think by default it is Gini. By default it is Gini. You can also enforce the algorithm to use information gain. And then you can compare with by fitting the decision tree with both the Gini as well as information gain, which one outperforms. You can check that one. See, nowadays the hardware cost is very cheaper. And most of the organizations now they have the Hadoop cluster. Right, so hence we don't have to worry about the parallel processing, all the things, right? The CPU cost, resource cost, you don't have to worry. End of the day, accuracy matters. That we'll see it later. I'll show you how to implement all these things, okay? And the next one is something called CHAID. CHAID stands for chi-squared automatic interaction detection. Both the Gini and entropy and information gain, those two techniques you can use it only for the binary split. What if I wanted to perform multi-way split? That is when CHAID is very much helpful. That is when the CHAID comes for our rescue. We know very well the formula for chi-square. Chi-square we discussed as part of inferential statistics. The actual minus expected whole square divided by expected, right? Square root of this one, right? Actual minus actual minus expected whole square expected, right? This is the formula we discussed it as part of inferential statistics. The higher the chi-square, that means that node will have to undergo split first. In the case of a Gini, lesser the Gini will have higher homogeneity. In the case of information gain, higher the information gain, that node will have, that node has to get splitted, right? When it comes to CHAID, higher the chi-square value, that one will undergo split. Look at this. This is my root node. Here I have 30 students. Of this, we have female node and the male node here. The left side we have male node, and this is my female node. This is my male node. This is the chi-squared formula. The observed minus expected whole square divided by expected. So if you look at the left side, left node, how many of them they play cricket? Only 2. The remaining 8 they don't play cricket. So in total 10 students are there. What is the expected play cricket? Chi-square we discussed, right? Expected play cricket. Out of the 10, 5 people are expected to play cricket, but whereas only 2 people played cricket. So 5 minus 2 is 3. 5 minus 2 is 3. Deviation. If you want to compute the deviation, play by cricket, this one, and expected not to play cricket. 5, this one, right? 2 minus 5. 2 minus 5. The actual minus expected or observed minus expected. 2 minus 5 is minus 3 and 8 minus 5 is 3. This is how we need to compute it. When you plug in these values, the observed and expected, you get the chi-square value here. Similarly, on the right side node, we have 20 male students are there. Of the 20 male students, 13 they play cricket. 13 they play cricket and 7 they don't play cricket. Overall 20 students are there. 20 male students and 10 female students here, okay? Of this, the expected play cricket is 10. The equal, right? In order to maintain the homogeneity, 10, 10, 10, right? So here the expected play cricket is 10, whereas it is 13 is there. 13 minus 10 is 3 and 7 minus 10 is minus 3. If you compute the chi-square value, how do you compute the chi-square value? This is the one, observed minus expected divided by expected, you will get 0.95. Okay, here the chi-square for the split is 4 point, what is this, chi-square for this split, right? So you get some value 4.5 or something like that. If you take another column, right, instead of using gender, right, let's say this is gender column, and if you use class column, if you compare the chi-square value for both the gender and the class, whichever column has higher chi-square value, that column will undergo further split. Here the high chi-square value means that the proposed split successfully to the problem into subsets with significantly different distributions. CHAID uses a p-value from a significant to measure the reservability, while CORT uses reduction of impurity measure. The CAID searches multi-way splits, right? So now we understood CAID algorithm is used to perform multi-way split, whereas the CORT algorithm, which is nothing but both the Gini and information gain, are used to perform binary split. The higher the chi-squared value will undergo the split first. Here I did not put for class. You can probably take the class. We have the data here, right? For Gini I used it. You can find out the chi-square value. Obviously the chi-square value will be more for the class, the gender, okay? The higher the chi-square value, that column will undergo split. When I use both all these techniques, whether it is CHAID or information gain, that one, right? It all same only, output is same only. The gender column has to undergo the split first in all the three things, okay? Next one is we have something reduction in variance. Reduction in variance algorithm is used in the case of regression tree. What do you mean by regression tree? To solve a regression problem. So far we discussed about the classification problem. To solve a regression problem, we have to fit the regression tree. In that case, the dependent variable is supposed to be a numerical or quantitative variable. In that case, the algorithm will behind the scene it use the reduction in variance. We know very well variance we discussed as part of descriptive statistics. The actual value minus the mean of this value, right? The x minus x bar whole square divided by n. This is what variance. If we take the square root on this one, which is nothing but standard deviation. The reduction in variance, this is the one is used for continuous target variable. To solve the regression problem, this is the one is used in the case of random forest. We'll discuss about random forest also a little later. The algorithm uses the standard form of variance to choose the best split. The split with lower variance is selected as criteria to split the population. Like Gini, lesser the weighted Gini, that column will undergo the split first. Similarly, when it comes to reduction in variance, lesser the column or the node which has lesser the reduction in variance, right? That column will undergo the split first. Let's take this example, okay, the same example. Let's calculate variance for each node, calculate each split as weighted average each node of variance. The same example. Look here, in this case variance for root node. Here, here 30 students are there. Of the 30, 15 students they play cricket, remaining 15 they don't play cricket. What is the reduction in variance for this one? How do I compute this one? 15 students, listen very carefully, they play cricket. Remaining 15 students, they don't play cricket. So those people they play cricket, I flag them as 1. Each person, right? For these 15 people, students, for each student I flag 1. Remaining 15 people I flag 0 because they don't play cricket. Okay, if I have to take variance, 15 into 1 plus 15 into 0 divided by 30 is equal to 0.5. The overall mean value, okay, because we need to know the mean value. Only then you can subtract from the actual x minus x bar. I need to know the x bar value. For the root node, the x bar is 0.5. And it is a bit tricky, right? 15 into 1 plus 15 into 0 divided by 30 is 0.5, and we have 15 1 and 15 0. Now variance would be, now you need to subtract this one from the actual one. 1 minus point. What is 1 minus 0.5? 1 is play cricket. 15 students they play cricket. I flagged each the 15 each and every person in the play cricket group 1, right? So 1 minus 0.5 whole square plus 1 minus 0.5 whole square, 15 times you have to do. And similarly, those do not play cricket. How many of them are? 15 people. 15 people, those do not play cricket, I flag them 0, right? So 0 minus 0.5 whole square, 0 minus 0.5 whole square, 15 times divided by 30. If you solve this, you will get 0.25. For the root node, the variance is 0.25. Next, female, and let's take female and the class 10, sorry, the gender node. Next one is, we'll look at the gender node, okay, gender node and class node. This is the overall thing, okay. Actually, this is the one is related to this one, okay. 30 students are there, right? That is the one. And the gender column, if you look at it, male and female is there, male and female, and 10 students, so out of 10, 2 play cricket, remaining 8 they don't play cricket. So those don't play cricket, I flag them 0. So 2 into 1 plus 8 into 0 divided by 10 is, because I need to find out the mean for the female node. Similarly, I need to find out the mean for male, and then only I can subtract from each and every student, female student, male student, isn't it? So here 0.2, and the variance is 2 into 1 minus 0.2 whole square plus 8. So what is 2? 2 students they play cricket. 2 into 1 minus 0.2 whole square plus 8 students they play. This is weighted reduction in variance, okay, and divided by 10 is 0.16. Similarly for male node. And then if you plug in this with the weighted variance of the gender column, you'll get 0.21. Similarly, I do the same thing for the class column also. So 0.25. Of these two, forget about this one, right? These two, which one is lesser? The gender column. The node which has lesser reduction variance, that one will first undergo the split, and then the next one will undergo the split. The same thing, even the case of Gini, weighted Gini, whichever node which has the lesser weighted Gini, that one will undergo the split first. But even in that case, Gini, when we use Gini, gender column was the one had to undergo the split first. Fine. So this is the one under the hood is used in the case of regression tree. Next, we'll try to understand ensembling model. Okay, so the spelling is ensemble, we spell it ensemble model. What is ensemble model? Ensembling model is nothing but we combine or we create multiple models and then we combine them to produce better result. Instead of relying on one single decision tree, what we do is we create multiple trees. And then we combine all the trees or all the classifier. Let's say instead of saying decision tree, I call that as a classifier. Instead of creating a single classifier, I am going to create multiple classifier. And then I combine all the classifiers. Based on the combination of all the classifiers predicted output, I am going to take the call. Right? Hence, the ensembling is nothing but it is a group of models. It not necessarily the ensembling is meant only for decision tree. As I told you, ensembling is nothing but creating multiple models and then combine them to produce a better result. For example, I created logistic regression model, support vector model, and then I created another model called neural network. Logistic regression, support vector, neural network. Let's see, logistic regression and support vector model. These two models, the predicted output is yes. Predicted class label is yes. And for neural network, the predicted class label is no. Okay? No. So in that case, one second. Let's say I have something called logistic regression. I created the logistic regression model to solve a single classification problem. I use three different algorithms: support vector, and I have something called neural network. Using these three algorithms, I am going to solve a single classification problem, but I am using different algorithm. Supposing I wanted to predict whether customer is going to default or not, right? So yes is they are going to default, no is they are not going to default. When I we create Rajesh. I wanted to know if I offer a loan to Rajesh whether he is going to default or not. I want to predict the class label for him, whether yes or no. So for that I am using these three models, machine learning model. As per the logistic regression, it says Rajesh is not going to default. As per the support vector, it says he is not going to default. But neural network, it says he is going to default. So in this case, we created multiple models and then we combine these three models output. Based on the majority voting, we decide the output. So these three models, two models says is not going to default. Right? Majority voting. Based on the majority voting, it is. So if it is going to be a regression problem, instead of doing the majority voting, it does the averaging. Supposing housing price, let's say you are using linear regression model, using support vector and neural network also you can solve the regression problem. Let's say you want to predict the housing price. Your linear regression model, logistic regression model, you cannot use it to solve the regression problem. Logistic regression is meant for classification problem. Let's talk about the regression problem. Let's say I want to predict the housing price. I'm going to use linear regression and I'm going to use support vector and neural network. Forget about logistic regression. I cannot use it. Housing price I want to predict. Of these three model, right? These three model predicted some price. Let's if for the given specification, 500 square feet of the house, what is the predicted housing price? My linear regression model says 1 crore, and my support vector says 1.2 crore, and my neural network says 1.01 crore. When it comes to regression problem, it combines all the models' estimated value and it performs the averaging. When it comes to classification problem, since the predicted labels are like this, you cannot perform averaging. It doesn't make any sense. It goes by the majority voting. It's something like, let's say your simple analogy is you are a project manager, you want to take your team members to a resort and you are conducting a voting. You don't want to be biased. The majority of the staffs, they say, your report is, they say, they want to go to a specific hotel. You go by the majority voting there, right? The same thing is the same analogy is applicable here in the case of ensembling. In the case of this analogy is for classification problem, okay? And also you understood in the case of in the case of regression problem, you need to do averaging. Remember this. So in the case of ensembling model, the advantage of this one is you don't have to treat the missing values. You don't have to address the outlier. If you have any outlier, you don't have to address it. Whereas in the case of linear regression model, it is sensitive to outlier. Even in the case of k-means algorithm or any clustering algorithm, if you have an outlier, it is sensitive. The model is sensitive to it. You have to address it first and then only you need to fit the model. But when it comes to ensembling model, minimal data preparation effort is sufficient. You don't have to spend too much of time in pre-processing data because it addresses all these issues. Okay, so using ensembling model, you can solve both regression as well as the classification problem. There are two types of ensembling. models are there. One is the bagging, other one is boosting. Bagging and boosting. What is bagging? When a regression method or a classifier has a tendency to overfit, right? Bagging reduces the variance of the prediction. Okay. What boosting does is it simply converts the weak learner to strong learner. The purpose of using bagging type of ensembling is to address the overfitting problem. What do you mean by overfit? My model performs well on the training data set. When it comes to test data set, it is not performing well. For example, my model, I'll take the linear regression solve, adjusted R squared or RMSE, root mean squared error metric. Okay, RMSE for the training data set is 0.33, but RMSE for the test data set is 0.83. The error is more for the test data set. When I train my model, so the trained model, when I applied the model to predict, and when I computed the RMSE, root mean squared error, I get lesser error. That means my model is performing well on the training data set, whereas on the same model, when I apply it on the unseen data, the error is more. Lesser the error is better. Here this is called overfitting. To address this overfitting, we use bagging technique. Okay, and boosting is to convert the weak learner to strong learner. Let's say the simple analogy is you are a project manager. You are identifying which all members are not performing well, and you are taking them and you are giving them the training. The same philosophy is, the same analysis applicable in the case of boosting. Why you need to train them? Because you want them, the poor performers, also to be a good performer. The same principle is applicable in the case of boosting. The example for bagging. So in the case of ensembling, not necessarily you have to use various other algorithms. When it comes to random forest falls under ensembling technique. In the case of random forest, we use multiple classifiers. The algorithm uses multiple classifiers, multiple trees. Instead of relying on one tree, it goes by the multiple tree. It is something like we are running a survey, election survey. If you contact more people, let's say you are running a survey with 50 people. Of the 50 people, 40 people, if they say, person A will win, what will happen? You go by the majority. Instead, if you run a survey only with 5 people, and if the 5 people randomly write, if they say person B will win, what will happen? It will mislead you, because you are running a survey with less number of people. The reliability very less. The similar other example is, if you want to buy a car, you want to buy the new Thor, right? They recently launched the Mahindra Thor, right? Thor model XUV. You contact your friends and relatives. You try to contact more people because you are investing more money. Based on the majority voting, you will decide. But in that case, right, you are relying on more number of people. You don't want to contact only 2 or 3 people. The same principle is applicable in the case of random forest. In the case of random forest falls under ensembling technique, but random forest is called as a bagging method. Okay, it's a bagging method. Random forest uses multiple decision tree. Instead of relying on one tree, it uses multiple tree. I guess the random forest create 500 trees during the training time. In Python, it creates by default 10 trees. But still you can specify. We have some parameter, hyperparameter. You can specify n underscore trees n underscore estimator. Sorry, n underscore estimator is nothing but number of trees. You can use 200, 300 and 500. We'll discuss about the fine tuning the parameter later. Okay, so at this moment understand that the random forest algorithm builds multiple trees. Okay, instead of relying on a single tree. In the case of CORT model, it uses only one tree. You have to rely on only one person. Instead of relying on one person, if you rely on multiple people's feedback, then whatever the decision that you are going to derive, that will be very valid, right? The same principle is applicable here. So in the case of random forest, how does it work? Look here. So in the case of random forest, it builds multiple trees. What we do is we train the model with, usually what we do is we train the model with training data. Here also we use the training data. Each and every tree, what it does is it randomly sample the data from your training data set with the replacement. Supposing, let's say you have, record, let's say you have 1, 3, these are all the index values, okay? 1, 3, 8, 10, 15. These 5 rows selected from the training data set randomly for this tree. For this tree, also randomly it sampled the data from your training data set, but there will be overlap between these two. Look here, here 138 is there, here also 138 is there, but 12 and 13 is not there here, but 12 and 13 is there. This is also called as bootstrap sampling. Randomly sample the data with the replacement is called your bootstrapping. Random forest uses bootstrap with aggregation. Okay. Similarly, for each and every tree, it randomly sample the data from your training data set with replacement. Number 1. Number 2 is, for each and every tree, it uses the different subset of the features. It uses the different subset of the, what do you mean by subset of it? For this tree, it uses these 3 columns, these 3 features. For this tree, it uses age similar to this one, but the remaining 2 columns are different from this one. For tree to tree, the columns are differing and the observations are also differing, but there will be overlap. But each and every tree has its own sample data and the randomness of the features are also there, right? So here number of child is there, but whereas it is not there. Feature randomness. This is called feature randomness. For each and every tree, the features also randomly selected. The samples also randomly the training data also randomly sampled with replacement. And finally, since it's an ensembling method, right? Let's say each tree predicted the class label as like this: yes, yes, no, 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 yes. Now you tell me, so what is the final predicted value? How the final predicted value will be generated? Supposing my model, I want my random forest model to predict whether Rajesh is going to default or not. This model says, this classifier says he is going to default, this classifier says he is not going to default, and so on. As per the ensembling technique, it combines all the models and then it goes by the majority voting, because in this case it is a classification problem. Now you tell me what is the final predicted value. What is the majority value here? 3 yes is there, 2 no is there. Yes is the majority, hence the final predicted outcome value will be, predicted label outcome value will be yes. Okay, that is why we call as the ensembling method. Now let us, I'll read out this bullet. Okay, in random forest we grow multiple trees as opposed to a single tree in CORT model. Randomly sample the data from training set with replacement. Each tree in a random forest can pick only from a random subset of the feature. In classification problem, the algorithm predicts the target class level based on majority voting, whereas in regression it performs averaging. Very simple. Random forest is very easy to understand, very simple one. Why it is called forest? Random forest because multiple trees. It creates multiple trees. That is the reason why it is called as random forest. What are the advantages of random forest? It helps to address the overfitting issue. You cannot say my model, let's say you are using a single classifier, single decision tree. You are using single decision tree to solve your classification problem. Your model performs well on the training data, test data set is not performing. You decide it is overfitting. But instead of relying on one model, if you use the random forest, right, it helps to prevent the overfitting issue. And using random forest, you can solve both classification as well as the regression problem. And the training time is less. Why the training time is less? Can someone tell me why it is less? Why it is less? Or can you tell me, are these trees are independent, or are there any dependencies between these trees? Are there any dependencies exist between these trees or amongst these trees? Is this tree depending on this one? Or is this tree depending on this one? Hello? Yeah, Rajesh. No, right? Yeah. Since these trees are independent of each other, right? You can you can train a random forest model in parallel, because this tree is the data set whatever is used by this tree is completely different from this one, though there is a overlap, but this data set is randomly sampled from your training data set, not from here, right? Training data set, this has drawn from training data set, this is also drawn from training data set. Hence each and every tree is independent. Hence we can train the rainforest or random forest model in parallel. The other advantage of random forest is you don't have to do too much of data pre-processing. It handles the missing values, and importantly, it performs the feature selection. Please remember. Training time is less and it performs feature selection. Yeah. And what are the hyperparameters are there in your random forest model? In the interview they'll ask you, can you tell me 5 hyperparameters that you have fine-tuned? N_estimator, this is nothing but number of trees in the forest. Random forest model, how many number of trees? You can specify the values here, okay? And maximum depth, max depth is nothing but the depth of the tree, and how many number of samples, what are the minimum samples to be split, and what is the minimum samples to be there in your leaf. All the values you can specify it explicitly. How many number of features, maximum number of features that needs to be used, that also you can specify it here, okay? These are all called your hyperparameters. Don't worry, when I give you a demo in Python, I will explain you in detail all these things. But at this moment, remember what are the at least if you remember 5, it will be reasonably good. So far we discussed about bagging method. Bagging method is nothing but the random forest, which it falls under ensemble technique. The next one is we are going to discuss about the gradient boosting. The gradient boosting is also another decision tree algorithm, okay? And the gradient boosting machines, we call it GBM, gradient boosting machines. This decision tree is extremely popular machine learning algorithm. It has proven successful across many domains and is one of the leading methods for winning Kaggle competitions. I discussed about Kaggle website, right? Kaggle website, they post all the real-time project related business cases with the real-time data. Right. So many of the Kagglers, they used gradient boosted decision tree to improve the model accuracy. So does that mean gradient boosting is the silver bullet? It's kind of. I'll just show you in the churn model in Python. You will get to know the power of gradient boosting machine or gradient boosted tree. The power of this one, you will get to know that. So how does this gradient boosted tree works? The gradient boosted tree, I discussed about the types of ensembling technique. One is bagging, other one is boosting. That time I discussed about boosting, right? What is boosting? Boosting, the central idea of boosting is convert the weak learners to strong learners. Okay. The gradient boosted tree algorithm, it takes an iterative approach to combine weak learners to form strong learners to increase the accuracy of the model. We take the weak learners iteratively and then we form the strong learners to increase the accuracy of the model. And similar to or like random forest, gradient boosted algorithm can be used for solving both classification as well as regression. But in general, both random forest and gradient boosted tree are used only for classification algorithm because it performs, you can expect more accuracy for the classification problem when you use these two. When you use regression, the accuracy is not that good. Like random forest, gradient boosted tree also outputs the feature importance, which all feature selection, okay, which features you are supposed to use it. As I discussed in linear regression, we used stepwise regression or right, and RFE also we used forward stepwise regression and backward stepwise regression to do the feature selection. But in the case of linear regression, we are building only one model. In the case of random forest, even the case of gradient boosting, we are creating multiple trees. Hence, if you go by the features recommended by the feature selection or the selected features recommended by the random forest as well as the gradient boosting is more reliable. But gradient boosting is very good algorithm. It outperforms the random forest algorithm most of the time. So how does this algorithm works? Gradient boosting, right? So how does this gradient as I told you, right, the central idea of this one is to take the weak learners and convert that as a strong learners. Look at this one. Here we feed the entire data to our algorithm. This is my boosted decision tree. Right, to make some prediction, I train this model with this data set. Let's say this algorithm misclassified some of the data. Let's say out of 10 customers, 7 customers it correctly classified, 3 customers is misclassified. Okay, now what happens is in boosting, right, it is paying more attention to the misclassified data points to increase the weightage. See what happens is in this case we started with a single tree, decision tree. We trained this with this data set. This model predicted the class label for 10 customers. For that, out of the 10 customers, 3 customers it misclassified. That means actually they are good customer, but my model wrongly predicted they are bad customer. So those 3 misclassified observations will be taken as an input for the subsequent tree. It's in the case of gradient boosted tree, it builds the tree sequentially, one after another it builds the tree. the subsequent tree in this case, right, it takes the misclassified observation from the previous or the predecessor tree, and then along with this it randomly sample the training data. Let's say your training data is there here, right? It takes not only, let's say you are taking only the 3 misclassified, but again you need to take the remaining data, right? Because you need to have the reasonable amount of data here. Randomly sampled data from your training data set plus the misclassified observation from your first tree, in this case this one. So now this tree tries to address the misclassified observation. It tries to correctly predict those 3 misclassified observations. There is no assurance even this tree can also address all the misclassification, right? Let's say it addressed only 2 misclassified observation by this tree, but still this tree has one misclassification is there. Next what will happen is another tree will get created, boosted tree will created, and this tree will take or pick up the misclassified observation from this tree along with the randomly sampled training data set. And finally what it does, it combines all the misclassified or the weak, these are called your weak learners, and then it will try to improve the classification accuracy. Okay, so what happens is, right, by doing this, by keep doing this until all your incorrectly predicted or misclassified samples are correctly predicted, right? That's how this algorithm increases the efficiency of the model. See, this model misclassified few observation. This model picked up these guys. It's something like in our project, right? We trained one guy and we asked him to complete one application. He made, when we tested his application, 3 bugs were there. We bring another guy. This guy picks up this guy's bug and he's trying to fix this guy's bugs. While fixing his bug, he might tend to fix only portion of his bugs, right? So another guy will come into picture. He will pick up this guy, and finally all these weak learners trees will be combined, okay, and then it will be correctly classified. As long as all the weak learners or correctly classifies, this one will be iterated. Look at this one. This is how it works. This is my decision tree 1, decision tree 2, 3 and 4. See, in the case of gradient boosted tree, the trees are built sequentially. Hence, you cannot train your boosted decision tree in parallel. Unlike random forest, GBM builds the tree sequentially. You cannot train this model sequentially. Okay. Now let us look at this one, how exactly this one works. You see the first tree, right? It classified these 2 instances correctly by drawing a boundary here. Okay, the D1 is the boundary, the blue colored one is plus, and 3 classes were misclassified. The subsequent tree, it picks up these 3 misclassified values, it assigns more weight. That's why you could see the magnified size of these 3 misclassified values. That means it assigns higher weight to the misclassified observation. It assigns higher weight to the misclassified observation. So what it does is, it is paying more attention to the misclassified data, right? So by increasing the weightage, it increases the weightage for these 3 misclassified observations in order to pay more attention to it. And then what it does is, the subsequent tree, right, since you gave more weight to it, these three were grouped together. But still See here, it has drawn a line here, but this one is there here, right? Still there is a misclassification here. There is a weak learner, weak learner, weak learner. And finally what happens here is, these two are plus, right? So here it gives more weightage to these two values, because these two are actually supposed to be here and this one was supposed to be here. So what happens here is, since it assigned more weightage to the misclassified observation, what happened, these two were combined together, and these two were combined together. Look here, with the combination of all these weak learners, right? So what happens is, it addressed all the misclassified samples, right? It's correctly classified. Now see, all the negative values are grouped together. There are no mix of plus and positive, plus and minus, right? This is how the the boosting algorithm works. Since the boosting algorithm builds the tree in sequence, you cannot train the model in parallel. Fine, hope you understood. It's a very simple algorithm, boosting also. Okay, and what is the difference between bagging and boosting? They'll ask you this question. Okay, so bagging is computationally more efficient than boosting, because you can train the bagging model in parallel, and bagging usually cannot reduce the bias, whereas boosting can. What is bias? Error. Boosting can reduce the bias. Why? Because each and every subsequent tree picks up the misclassified observation from the previous trees. It tries to fix all the misclassified observations. Hence, the bias is less in the case of boosting compared to random forest. In the case of random forest, in case of any misclassification, it is not addressing it. It simply uses multiple trees and it goes by the majority voting. But bagging usually performs better than boosting if you don't have a high bias and only want to reduce variance. If you want to reduce only variance, then you can go for bagging. Or if your goal is to reduce the bias, then you can go for boosting. So all is well. Random forest is good compared to random forest. Obviously boosting is outperforming it, because it is trying to correct all the misclassified instances or observations. But boosting is the gradient boosted decision trees in practice, in real time. If you want to extract any insight, it is not that easier. Okay, that is the reason why there is a trade-off between random forest and boosted decision tree. Okay, but if your goal is you want to increase the accuracy, then go for boosting. But if your goal is more on I want to extract more insight, then you can go for random forest. But both random forest and boosting algorithms are good for solving classification problem. Though you can use it to solve, you use these two algorithms to solve the regression problem, the accuracy is not good when it comes to regression problem. Any questions so far? Very simple, right? But you need to remember a couple of things, because since you're all attending first time this topic, you need some time to understand, recollect. Okay, I hope all of you must have understood, right? How many of you are still not clear? Okay, since I did not see any no, I assume most of you understood, but still you need to revisit. You watch my video, I'll upload it. Fine. Now let us quickly get into Python and see how to implement the random forest and gradient boosted decision tree. See the churn analysis final. This is the final one. Okay, since I'm using this a working copy, I use different naming convention. Okay, don't think this script is different, that script is different. It's all same only. This one already uploaded in my GitHub. For the benefit of you all, I'll share the link once again in the chat window. I'm going to share this one. You can go and download the scripts from here. Okay, you go to machine learning, you can find all the scripts and data set also. Churn analysis final. Okay, you can download this one, and then we have some pychurn.csv. that is the data set you are supposed to use it. And even for gradient descent it is available, right? So gradient descent, yeah, it is there. Gradient descent also I upload the script. Okay, okay, so this is where you need to download my script and the data set. I shared the link in the chat window. Okay, sorry, I sent it to him only. I'll send it to all. Okay, you just copy paste that link which I sent it in the chat window, so that you can download the script and data set to start practice it. Okay, now let us look at this one. Okay, how to implement. I imported all the packages like NumPy, Pandas. These are all the data visualization package, and this is to overcome the warnings which gets displayed unnecessarily, right? So I use this package, and NumPy, Pandas you know very well, and sklearn is the scikit-learn. This is the machine learning package used in Python to implement most of the algorithms. Okay, neural network and cross-val score, random forest classifier. Look here, random forest. So as part of sklearn.ensemble, random forest classifier is available. You need to import it. And gradient boosting classifier, this is the one we are supposed to use it. And confusion matrix, log law, these are for metrics purpose, and this is for resampling and smart. This I will discuss it with you all later for Rajesh and others. Okay, so this is my data set. I imported my churn data. This is a churn data set. I imported my churn data set. Here I could see these many number of columns are there. This is my target variable. I did little bit data preparation here, because here I have categorical variable. I converted this a numerical variable, because in the case of logistic regression also all your independent variables are supposed to be numerical, right? So hence, but here I convert as a binary values. Wherever no is there 0, yes I mentioned 1 here. For this I used something called label encoder. Okay, as part of pre-processing, there's something called label encoder method is available. And here what I did, fit transform, le.fit transform. You need to do this on top of this data frame, right? Data frame is df2. For these 3 columns I want to convert this as 0 and 1. Wherever no is there, you replace that by 0. Wherever yes is there, replace that by 1. And even for false, the same thing. Okay, after I did this, look here, it is very much handy, especially if you have more categorical variables. You have to use multiple if-else condition in order to do encoding manually. But here, with the help of this package, in one go you can assign zeros for no and yes for 1 for yes. Even if you have 50 columns, in a matter of a jiffy, it will perform the encoding. Look here SS is there, it made is a 1 1, right? Here 2 no is there, right? So that is how it is. Now what I did, I have overwritten these 3 columns. So I have overwritten the older 3 columns with the new columns. So now I don't have yes no here, instead 0 1 1. In the last column is the dependent variable. Here also you can see 0 1, but here I displayed top 5 records. And the next one is, you can ignore this one, and here this is important step, train test split. So on the right side, right, see here I imported the train test split from this package, and this is mandatory. You need to use 4 arguments, okay, 4 parameters to hold the training dataset dependent variables, and then the training dataset the label, and the test dataset dependent variable, and test dataset label. And right, to hold this you need to have 4 variables by default, okay, because this function on the right side, this method, this returns 4 different values. Here what is xy? X is nothing but the independent variables, all the independent variables. Y is your dependent variable. Test size equal to 0.35. So what why I mentioned here is, split the given data set. This is my original data set. My original data set, the data frame name is df. The given data set, you split it with this ratio. The train and test split ratio is supposed to be 65-35. My training data set is supposed to be 65% and test data set supposed to be 35. That means randomly sample 60% of the data for training data set, randomly sample 35% of the data for test data set. Fine. Forget about this one, okay. If you watch my video once again, you will be able to understand. Now let us directly jump into the decision tree. Look here. So here I fitted only one single decision tree. Instead of using random forest and gradient boosted decision tree, I used the single tree. Here I trained a single decision tree classifier. Okay. So how do I, if I want to train a single decision tree, how do I do that? This is how we do it. Usually we work only with random ensembling technique, the random forest or the boosted decision tree. We never use single decision tree, but still to understand that I included here. Import the decision tree classifier from the tree package, the sub package tree from your sklearn. Create the instance for this, and then next train the model. This is common for all the most of the supervised machine learning algorithm. Okay, first you need to initialize your model, in this case the decision tree classifier, and then the d-tree dot fit, right? So here you need to train the model, initialize and train. So then now I fitted the model. The next step, I want to check the score. There is a score method that is available as part of the metrics library. Simply you specify d-tree dot score. You need to specify all your independent variable for a training data set and the labeled data for your dependent variable. In the training data set, you need to specify here. Basically, I wanted to understand what is my accuracy on the training data set and test data set. See, I am applying my trained model d-tree on the training data set itself, and also I am applying my trained model d-tree on the test data set. With both training and test data set, what is the accuracy? If I look here, the score train and test is, look here, this is the one, right? The model there is a overfitting here. Overfit. So what do you mean by overfitting? My model accuracy is 1. In real time scenario, you cannot get 1 and all. But it says the accuracy is superior, 1. for the training data set, whereas the test data set, the accuracy is 0.88. The difference between these two are, substantially high. Okay. Ideally, these two, the training and test data accuracy, somewhat closer to each other. There should be variation, but it should not be too much. So that means my model performs well on the training data set. In the test data set, it is not performing well. There is a overfit here. Okay, for illustration purpose, I just showed you how to implement a single decision tree classifier. Okay. Next, to view it, to visually see the decision tree, in Python we have only one package that is available, py.plus. Simply you execute this line. Okay, I just already put exclamatory here, pip install py. This package will get installed. It will take some time. Once you see this, next what you do is import all the things. Okay, graph is, everything is available as part of py.plus. Okay, and then what you do is, next step is simply when you execute this one, it will display the tree here, the decision tree. When you double click on this, it will show the magnified view of this one. Okay, so in this case I use churn data. It shows, once again, or you can store it on a PDF file also, or you can specify the size also, the image size and all, or let me just minimize it. Okay, it got minimized. So this is my root node based. So look here, in real-time scenario, when you look at the decision, it will be like this. It is not as easy as how I showed you. This is just for illustration purpose I showed you. But in real-time scenario, if you have multiple columns, the business logic, or if the data also has more structure in it, patterns in it, your tree will be like this. Okay, this is for a single decision tree. I did not create multiple decision tree. Using decision tree classifier, I created only in single tree. Now let us see how to create multiple trees using random forest classifier. Random forest classifier, inside the parenthesis I mentioned n underscore object equal to -1. So what this one says is, train this algorithm in parallel. The -1 value tells build this model in parallel. Okay, so here I initiated the model, right, initialize the model, and the next one rfc.fit. Here I am training the model with the training data set. This is the one is holding all the independent variable. This is the one holding only my dependent variable. Okay, I train my model. Look here, by default it uses Gini. Okay, or you can specify here also explicitly, comma, criterion equal to entropy, something like that. Okay, if you specify like this, it will use that splitting criterion. Okay, these are all the parameters. These are the parameters, like how do we validate decision is correct or not? If we have multiple models, is it by Gini or GAIN? Yeah, the validating the model I will tell you how to evaluate the model accuracy, right, Bhupati? I will tell you. I have not yet gone to that step. Okay, look here. If we train my model, these are all the default parameters. Bootstrap equal to true. That means randomly sample the data with replacement. Okay, and criterion Gini and max depth and auto. All these are all your parameters. N underscore estimator is nothing but number of trees. Yeah, sorry. In the case of Python also, by default it creates 100 trees behind the scene. 100 decision tree it got created behind the scene in a matter of second, right? It creates 100 trees. But in this case our data is less. If you have huge volume of data gone, sometimes it will take 3 to 4 days also to train your model, especially when you deal with millions of observations. It takes 2 to 3 days at least. Even when you work with clustering, all the things, right, still it will take. But even in the case of clustering, we cannot get access to in the case of development environment, right? They will set some quota for the developers also. So these are all the hyperparameters. Okay, and the next one is, look here, and next what we will do is, let's go step by step. look here, in the case of, okay, what I did, instead of fitting the model just like that, right, random state equal to 1, look here, I don't want 100 trees to be created by default, because to create more number of trees, it requires more system resource and it will take longer time, especially when you have huge volume of data, it will take longer time. Hence what I do is I can override this value also. I can override the default value 100 by 50. Whatever value you can specify. Max depth, you can specify your own value. N underscore jobs equal to -1. That means train this model in parallel. Okay. So now what I am doing is I am going to I'm going to train my model once again, because I mentioned various values here inside this one. The reason why I retrain the random forest classifier here is I want you to understand how you can explicitly override the default hyperparameter values. Okay, and now what I do is I train my model. Next, in the case of the model, once you train your model, right, R of dot feature underscore importance is underscore. With this, you can find out the optimal number of features or the best features that you can use it in your model, right? That is recommended by your random forest. Random forest recommended the best features. What do you mean by best features? The features which have higher predictive power. Here using this plotting option, right, I plotted it here. By looking at this, the day charges, total day minutes, customer service calls, in these three columns, if you include it in your model as an independent variable, it is very much helpful in terms of predicting your outcome variable. With these three columns, you can increase your model accuracy. So, but still you might be asking, so here these three columns are superior, even including this one, right? So even international plan also you can include it. But the rest of the, as you go, when you look at this side, these columns have lesser predictive power. And just by looking at this itself, you will get an idea. Okay, or probably what you do is 3 and 6 columns you include in your model and check your model accuracy. So using score we can check. Bhupati, to answer to your question, we have a function called score, right? So this is the one will give you the accuracy, how accurate your random forest model, 0.937. It's very good here. So I'm going to build the confusion matrix. Here's something called confusion matrix. The confusion matrix is similar to the one we discussed in hypothesis testing. I hope you remember, right? What is type 1 error and type 2 error? Look here. See, we are talking about the churn. What is churn? We are interested in finding out which all customers are more likely to leave my business. Okay, 0 means they are not going to leave my business. This is my actual, this is my predicted. Actually 561 people are not going to leave my business. My model also correctly predicted 561 people are not going to leave my business. But when you look at here, the diagonally, so 43 people are actually they churn. My model also correctly predicted they are going to churn. What is this 36? 36 people are actually churned, but my model wrongly predicted they are still with us. They are still with us. Already these people left. But here, what does it say? Actually, these 4 people are still with us, but my model wrongly predicted these people, these 4 guys, they walked out of us. Fine. Ideally, this diagonal, right, the 36 and 4, these values are supposed to be lesser the false positive and false negative, it is better. Okay, it is better. Fine, let us see with gradient boosted decision tree, right, the values for these two. Next, what we will do is we will check the future importances, but instead of viewing it in terms of numbers, I just plotted it here. Okay, the higher the value here, those columns which have higher values, which is 0.044 0.04, 0.03, 0.08. Yeah, here it did some kind of sorting and all. Okay, the total day charges could be the higher the value of all these things, right? Yeah, 0.101, 10, yeah, 104. Maybe this is the one is for the first column, the total day charge. Okay, the higher the future importance value, that means those columns are very much helpful in your model. Include those columns in your model. That is what it tells us. Those columns has very less value, that means don't include those columns. So using random forest, you can do feature selection. Real time scenario, we use random forest also to do the feature selection. Even in the case of logistic regression, stepwise regression is available or RFE is available, but still this is more reliable. The random forest feature importances or the features which you selected based on the random forest model recommendation, it is more reliable. Similarly, gradient boosted decision tree recommended features are more reliable, but compared to random forest, the features recommended or the features selected by the gradient boosting is more accurate, more, very good, right? More reliable. Look here, next I'm going to initialize the gradient boosting classifier. Okay, use 500 trees. All these things I mentioned it. Learning rate is kind of regularization, you ignore it at this moment. Okay, and I'm going to train my model, and my training and test data set accuracy is somewhat closer, right? So 0.94, 0.10, and the future importance, you can use the same, you just copy paste it to visualize the features recommended by gradient boosted decision tree here. Okay, and confusion matrix, I did not use it here. Yeah, you can compare the confusion matrix also with this one and that one. I think I did it already. Okay, so what you do is the assignment, you take my script, right? And here RFC is my random forest model name, but in the case of gradient boosted tree, GBC is the model name. GBC dot predict, apply the gradient boosted. In this case, I applied the random forest model on the test data set to make a prediction, right? So PD dot cross tab and your test data set, the dependent variable, this is the actual value. This is the actual value, predicted value. The actual maybe, right, some customers are non-churners, but my predicted model should also be non-churner for some customers. Okay, let's say for Rajesh, Rajesh is actually non-churner. My model also correctly, my model should also correctly predict Rajesh is a non-churner. If it is not correctly classifying it, then you will see more values in this side, false positive and false negative. Okay, ideally the false positive, false negative should be less, but there are cases you don't have to worry too much on the higher values of the false positive and vice versa. Depends on the domain which you work on it. I already discussed about it, and Rajesh and others, right, I'll discuss it for you separately, don't worry. Confusion matrix we'll discuss later for you people. Hope you understood as of now how to okay, so Bhupati, your question is how do we validate the decision is correct or not? Using the score, right? Score, and you have something called area under the curve, ROCAUC. I'll discuss it later. Okay, after I complete the metrics part for you people, we'll discuss about that. And answering to your other question, if we have multiple model, is it by Gini or gain? Super. See, when it comes to, it's a very good question. When it comes to classification algorithm, we have something called metrics called accuracy, and we have another metric called precision and recall. Let's say I use 3 different models, logistic regression, random forest, gradient boosted tree, neural network, for all these models, the classification metric is same, but the value for each model's metric, the metric values for each model will be differing. Okay, but the metrics are same for all the classification related algorithms. That is why learning machine learning algorithm is very easier. Once you understand the metrics related to classification algorithm for a specific model, the same thing is applicable for all the other models, all the other classification related models. Bhupati, are you getting it? If you have multiple models, okay, multiple models, is it by Gini or gain? No. Gini or gain, information and gain and Gini is applicable only for the binary split, the two for the decision tree, random forest or gradient boosted decision tree only you can use it. You cannot use Gini or gain for neural network or something else. Okay, neural network, support vector machine, or graded or Naive or logistic regression, you are supposed to use accuracy or precision or recall. I repeat once again: precision, recall, F1 score, accuracy. Only these four will be used to compare multiple classification related models. But these four metrics are common, but the values differ from one classifier to another classifier. But the Gini and information gain is specific to decision tree only. Random forest and gradient boosted tree only it is applicable. Got it? And that too, Gini and information gain, you are supposed to use it only for the binary split. Fine, Bhupati. Any other questions? Yeah, with this I'll wrap up. Tomorrow we'll cover other loose ends. Okay, if any other things other, we'll cover it tomorrow. I thought of covering the coding part tomorrow. We are well ahead of the schedule. Good. But still, we will use tomorrow's time in a very useful way. Okay, by covering other algorithm, not a problem. Any questions so far? Okay, since you don't have any other questions, I'm going to end this session. We'll share the video. Script is already there. Data set is also there. Only thing is video, I'll share it. And this PowerPoint, I made a lot of changes. I'll upload this one probably in 2 to 3 days time. Okay, in my website. All right, fine. Okay, good night. Take care. We'll circle back tomorrow same time. Okay.